All right. Well, let's go ahead and kick this thing off. I think there are probably a few more who will be joining us, but I want to be respectful of everyone's time, so we'll go ahead and get started. So welcome everyone to the Oklahoma City Innovation District Student Showcase on Autonomous Systems. This is actually the second part of a two-part series, a wonderful partnership that we have had the opportunity to be a part of with OU School of Meteorology and their CAS initiative. And so we're very grateful to Dr. Chilson and Dr. Liz Little for welcoming us into this partnership. Super excited about today. A couple of housekeeping items. This is being recorded, so hopefully on down the road we can share this content and share the excitement around this research. If you don't mind, I think everyone is muted, but just if you can keep yourself muted until we get to the Q&A, just to help cut down on background noise. And speaking of Q&A, once we get to that portion, if you would like to ask a question, that is wonderful. Just we only ask that you please introduce yourself and tell us a little bit about kind of where you work and the area that you're focused in, so the students and we have a little bit of context. So here at the Innovation District, our role really is to connect different industries, connect different offices, different working professionals who have an interest in networking and programming and are looking for opportunities to connect in ways that they otherwise might not be able to. As many of you know, we had planned to hold our 2020 annual symposium on the topic of autonomous systems in April, but had to unfortunately cancel due to the pandemic. And so we've been working on transforming some of the presentations that would have happened at that conference to a virtual format, which is what has brought us to this series. So we are so excited to be showcasing and bringing visibility to student research being done in the area of autonomous systems. And again, thrilled to be working with OU on this. So with that, I'm going to go ahead and introduce Dr. Phil Chilson, who will tell you a little bit more about CAS, the Center for Autonomous Sensing and Sampling at OU, as well as introduce the two students who will be presenting today, Brian and Gus. So Dr. Chilson is the director of the University of Oklahoma's Center for Autonomous Sensing and Sampling. In this capacity, he strives to promote the culture of interdisciplinary and team-driven research to improve how we use emerging technologies to investigate, monitor, and ultimately better understand the environment in which we live. He's also a professor at OU School of Meteorology and leads research in the center focused on thermodynamic and kinematic structure of the atmosphere boundary layer. His current research interests include investigations in atmospheric boundary layer, aeroecology, and the advancement of remote sensing technologies. He received a BS and Ph.D. in physics from Clemson University and an MS in physics from the University of Florida. So with that, Dr. Chilson, I will hand it over to you.
Yes, thank you. We're delighted to have everybody join us today, and we're also delighted to showcase two of the students in a group. As we've heard, the Center for Autonomous Sensing and Sampling is all about trying to find innovative ways of using autonomous systems, robotic systems. These two applications focus on the atmosphere, but we are interested in a variety of applications for water bodies and ground-based and what have you. And we're a relatively young center. We were created in April of 2016. And at the risk of sounding extremely cheesy, I will say that what we value the most about our center is the people that we have. And I'm really delighted to be able to introduce the two speakers that we have today. So let's start with Brian Green, who's going to lead off. He comes to us from the University of Illinois, where he did his undergraduate degree in atmospheric studies and physics. He got his master's degree in meteorology at OU, working on UAS topics. And now he's pursuing a PhD, and he's been doing great work looking at various facets of the lowest atmosphere. And so without stealing his meteorological thunder, I will let him take it away.
Awesome. Let me go ahead and get my screen sharing started. Can everybody see this? Good? Okay, sweet. So again, thank you all for that introduction. Thank you for the opportunity to present here today. Presenting remotely under these crazy circumstances is, I think, still an awesome opportunity. So today I'll be talking about the Arctic stable boundary layer from the context of a field campaign we were able to participate in Finland in 2018. So I have a couple alternate titles. It's really mentally confusing and draining to study the Arctic when we are in the dead of summer in Oklahoma. Furthermore, looking at this data from Finland makes me think about how it looks like they've been really good at containing their COVID-19 outbreak, but all of this considered, my wife still doesn't really want to move to Finland. So on we will pursue with our studies from good old-fashioned Oklahoma. So to everyone here, it might not be too much of a surprise, but the amount of observations in the atmospheric boundary layer, or again, the lowest portion of the atmosphere, is severely undersampled. Several federal and international communities have come together recently to highlight some of these deficits in previous years, and there's been a pretty big push for improvements to sensing capabilities. Moreover, there are really important linkages between studying the Arctic weather and the ability to improve forecasting in the mid-latitudes where we all live. Turns out that if our models can do better in the Arctic, our forecast skill gets better where we live. So understanding some of the dynamics of what's going on there is highly influential to our day-to-day lives, understanding the weather here. Moreover, it's really difficult for these global forecast models to be able to accurately predict turbulence in stable boundary layers because the scales of motion are maybe a couple meters, whereas the models themselves have grid spacings of tens of kilometers. So they have to rely on a ton of different types of parameterizations that are not always very good or even developed specifically in the Arctic boundary layer. The Arctic is also incredibly sensitive, more so than the rest of the Earth, to anthropogenic global warming. Many studies recently have shown that temperatures are increasing several orders of magnitude more than the rest of the globe, largely related to the really intricate balances of forcings and radiation with sea ice that melts off and refreezes every year, and ocean currents that disperse energy throughout the globe. And then more recently, we've some studies in the Arctic have linked some energy balances related to the presence of low-level mixed phase clouds, which were previously not necessarily believed to be there, which plays an enormous role in how global climate models are able to represent the energy budget for hundreds of years into the future. So better understanding some of these processes is a large driver behind what I will be talking about today. We'll be focusing on the field campaign known as ISOBAR, which stands for the Innovative Strategies for Observations in the Arctic Atmospheric Boundary Layer. This was a 1-month-long campaign that took place twice in 2017 and 2018. We, as members of CAS, were able to travel for the 2018 campaign, which I will focus on more. This took place on the island of Hailuoto, Finland. So for those of us with not great knowledge of Northern European geography, which I didn't before this campaign, here's a map of Finland, Sweden, and Norway. And the pin right in the middle there is just off the western coast of the country of Finland. We zoom in a little bit, you can see the major city of Oulu and this island of Hailuoto, which we were centered on the western portion of, which in this Google Earth image looks like a nice tropical paradise, but that was pretty far from the case since we were there in February. It was nothing but sea ice for a kilometer or two off the coast, pretty homogeneous terrain with a perfect opportunity to study some Arctic stable boundary layers. So some of the instruments, for a little bit of context that we had a 10-meter tower with a bunch of awesome sensors, high resolution, high accuracy and precision sensors at multiple levels. We also had another 2-meter tower, a little bit displaced from the main 10-meter tower. And we would primarily fly our drones near these towers, which were operating continuously for about a month. We also had 2 SODARs and a LiDAR wind profiler in order to get a 3D depiction of the winds in the lower boundary layer at a much higher resolution than we could get from just flying periodic profiles. And these offered really high quality data in order to compare and contrast some of our measurements from the main attraction, which are the UAS or RPAS, unmanned aircraft systems or remotely piloted aircraft systems. These acronyms are thrown around all the time. And this ISOBAR campaign was really one of the first field campaigns to feature the usage of drones in an Arctic study. So we had 2 main flavors. That was the rotary wing aircraft on the top left. That was our OU Copter sonde. That was a generation or a half a generation predecessor to the drone that Tony Segales talked about 2 weeks ago. You can see some similarities if you were on that call last time. We would fly this one from the surface to about 300 meters every 20 minutes or so throughout the night to get a really good evolution of the boundary layer thermodynamically and kinematically. We would fill in higher profiles up to 1,800 meters with the fixed wing aircraft, which is on the bottom right there. That was the SUMO, stands for Small Unmanned Meteorological Observer, I believe. We had airspace permissions to fly up to 1,800 meters, basically whenever we wanted to, just by effectively texting some local authorities in Finland, which made it a really ideal opportunity to study the atmosphere in this remote location. So here's a quick map. I think this is some satellite imagery taken from a paper that we have in review with BAMS right now about an overview of the campaign. You can see this little red shaded region. I apologize that this is not colorblind friendly, but this is primarily where we were operating our rotary wing aircraft, and the location of this X and plus are where the towers were. So you can see it was a couple, maybe about 100 meters off the coast or off the shoreline where we were flying just vertical profiles continually. So this leads me nicely into more specifically what we will be talking about today, some science questions, namely, can we match the net long wave radiation distributions during the ISOBAR campaign to previously documented field studies such as the SHEBA campaign, which was a really large effort by the US government in the late 90s, one of the most forefront Arctic research campaigns to date. Can we also relate this distribution in net long wave radiation to the presence of low level mixed phase clouds? And how does the lowest 200 meters of this stable boundary layer respond dynamically to this reduction in radiational cooling? So to get started, let's look at the distribution in surface net long wave radiation. So just a little bit of background. The Earth cools primarily via long wave radiation, and in the Arctic boundary layer, when it's perpetual nighttime, the surface can get dramatically colder than the air directly above it. Even with ice phase clouds, or like cirrus type clouds, are mostly invisible to the infrared spectrum. However, mixed phase clouds, or ones containing liquid droplets in it as well, emit their own net radiation, or their own long wave radiation back down to the Earth's surface, which can dramatically reduce the cooling effect by the Earth's surface. So this is reflected in this histogram of just all of the surface net long wave radiation during the campaign. You can see this peak close to 0 watts per meter squared is likely related to the presence of some type of forcing that's not allowing the surface to cool as rapidly as it would like to on the left side of this vertical line, where you see 2 smaller little peaks that are probably cases where the surface, or where the clouds are not present, allowing the surface to cool. And we see a pretty distinct cutoff around 25 watts per meter squared. So keep that in the back of your mind. I'll be using that cutoff as we move forward with some composite analyses. So we know that this exists. Can we somehow link more explicitly the presence of low-level mixed phase clouds? We know that this might be a driver, but I will now show you some 2D histograms with cloud base heights from a solometer located on the island as well. So on the left-hand side, or on the y-axis, is a distribution of cloud base heights, and on the x-axis is the same distribution of surface net long wave radiation measured by our tower. And you can see a couple distinct peaks here. I want to first look at this one in the lower right-hand corner. So this is really low-level cloud base, so below 1,000 meters, and really low surface net long wave radiation. So this is, again, an indicator or a type of fingerprint analysis of the presence of low-level clouds that are directly impacting our surface energy budget. I apologize for the color bar. I didn't get trying to change it to make it a little bit more better contrast. But there is also a secondary peak here at about 3,500 meters that extends across a lot beyond cooler than that 25 watts per meter squared cutoff there. These are higher level clouds, possibly mixed phase, possibly ice phase, if they are allowing for negative surface cooling. And then there's a small peak closer to the ground of lower level clouds with still strong surface cooling. We can also measure the effect of low level clouds based on how the temperature profiles are measured by our drones throughout the campaign. So if the surface cools faster than the air above it, we expect temperature to increase with height pretty dramatically. So this x-axis on here is low level stability. I've defined that just as the difference in the top and bottom of a profile over about 250 meters on average. And the y-axis I shifted to be our surface net long wave radiation again. We can see a couple peaks here again. There's this one with weaker low level stability and close to zero net long wave cooling. So this is another fingerprint of the presence of low level clouds reducing the overall low level stability in the atmosphere. We have another peak in the bottom right-hand corner. So this is the strongest surface cooling and the strongest low-level stability. This is our classic case that we would expect for clear skies, allowing the surface to cool really strongly and getting strong low-level increases in temperature with height. And then we also have this middle peak here somewhere in between. So we have weaker stability, but also medium-range surface level cooling. And basically, we can, with all of these factors combined, we can somewhat confidently say that this peak in net long wave radiation close to zero is likely related to low level clouds that end up warming the surface and reducing the amount of stability in the atmosphere. So if we look at this from a more composite perspective, from the actual profiles from the UAVs, let's go ahead and look at how the boundary layer responds dynamically to the reduction in surface radiational cooling. So here are some composite profiles of left temperature, middle specific humidity or moisture, and on the right is just wind speed. Note that the y-axis is split in the amount of stretchiness somewhere in the middle. So the lower portion of the profiles are only from our Copter cases, and the upper portions are from the fixed wing aircraft that are able to fly up to 1,800 meters. In the blue are the cloudy cases denoted by that negative 25 watts per meter squared cutoff in surface radiation, and the red lines are our clear sky cases. So there's a lot to digest here, and I could spend a very long time dissecting things, but just I'd like to point out the temperature profiles in the red versus blue. You can see that temperature generally increases with height more strongly in the lowest 100 or 200 meters or so, compared to this blue line, where we see temperature actually on average will decrease with height in the presence of low level clouds, which is not something that one might expect when they're standing out there in the freezing cold during a field campaign in the Arctic boundary layer. So these are very interesting observations that have never really been seen before on this level of detail. You can also see some interesting peaks in the moisture profiles with height in the lowest levels, a strong increase with height on top of a generally weak increase with height in the cloudy case, somewhat probably related to the advection of moisture off of the sea in and out throughout the evening. Okay. Another way we can dissect this is kind of digging into a little bit of turbulence theory. I'll try to keep this somewhat brief because I know not everyone has the stomach for turbulence on a Thursday afternoon, but suffice it to say that in general, this methodology, first kind of introduced by Sorbian in 2010, showed that you can basically relate vertical profiles of turbulent mixing in momentum and heat can be related to just these simple 3 scales. So the height above ground level, the change in temperature with height, and your overall buoyancy in your profile. This is a very big difference, but also fundamentally the same, paradoxically, as traditional Monin-Obukhov similarity theory that scale turbulence using surface values of turbulence, which inherently presents a lot of problems in the stable boundary layer. But suffice it to say that if we instead use these types of scales and look at the vertical profiles of Richardson number, which is effectively just change in temperature over the change in wind speed versus height as a ratio of stability in the atmosphere, we can unlock a lot of really interesting relationships. So if I grab a case study of a somewhat nice profile from the perspective of clear skies in our campaign, we can see that we see some pretty common features in a stable boundary layer here. Temperature increasing with height, moisture increasing with height, and the presence of a low-level jet in between all of this. So I want to focus on this level at the top of the inversion. If I go ahead and run through some of this scaling analysis, we can see that a lot of turbulent mixing, which is in this middle panel, is confined to the level below the top of this inversion layer in both momentum and heat. And I'd like to contrast that to a cloudy sky case where we have a pretty well mixed layer and then an inversion all the way up at 125 meters instead of a surface-based inversion. And then you can also see the presence of low-level mixing is then confined to almost the lowest 50 meters or so in the atmospheric boundary layer here, which is a pretty big difference from the clear sky case. So these are all some pretty preliminary studies. There's still a lot more to do with tinkering this methodology, but we can already start unlocking a lot of really interesting features of these differing types of boundary layer regimes that have a ton of implications for global weather understanding. So again, to take a step back, what we've learned from all of this today is that our observations do match with other large-scale field operations, which is already a good sign. Just a checkbox at the beginning to know something we're doing is right. At least these data have something useful in them. And the way we've associated the presence of low-level clouds with low-level weak mixing could be a really interesting perspective on the global energy balance and how global climate models and regional weather models ingest these types of data. So I will go ahead and leave it at that. I'll leave my summary and conclusion slide up, and I would be more than happy to take any questions you may have at this time. Thank you all.
And just a quick reminder, anyone who jumps in with questions, if you wouldn't mind kind of stating who you are and where you work, just so that we all know who each person is. Brian, you must have answered all of their questions. Nobody?
I guess I'm that good, or it was just so confusing, it was beyond hope.
Any questions? Yeah, go ahead.
Yeah, my name is Rod Vargas. I work for the FAA. I was just curious about the the flying ability on such a terrain where you were, what changes or differences you noticed there versus here in the United States, in Oklahoma weather, and if you had to do any kind of modification on your sensors, because of the difference in, I guess I assume you probably will have to calibrate there. Thank you.
Yeah, that's an awesome question. Thank you, Rod. So one of the biggest differences for us was the presence of icing. When there were these low-level clouds, flying our quadcopters into them, which was allowed. Thankfully, we were allowed to fly beyond visual line of sight. We did come down with some decent amounts of propeller icing in some cases, which thankfully did not impact our aircraft's ability to fly too much. Landing the fixed wing aircraft was actually pretty easy because we had, well, I wasn't the one flying them, but Tony Segales is on the phone here too. He was one of the primary pilots, but it was, if anything, having all the wide open space was nice for our aircraft operations. Keeping the sensors healthy was a difficult challenge because coming inside with the sensors would allow the opportunity to just condense a ton of moisture on the electronics coming from the super cold to any type of indoor environment. So we had to be very careful with that. We actually wound up leaving the copters outside during our observational periods. And whether or not that was enough, we'll probably never know for sure. But we did do a little bit of calibration on one of our off days. We were able to do some sensor response testing in the saunas conveniently located because we were in Finland. They had saunas on site for us. So we could take it from the 100 degrees Celsius inside to the 0 degrees Celsius outside. And the sensors seem to have remained healthy throughout the campaign. But I can let the engineers speak more than that.
Thank you, Brian.
Mm-hmm. Cool.
Other questions for Brian?
Yeah, I have one more, if I'm allowed.
Sure.
Did you see any microclimates out there in that environment?
Yeah, sorry, go ahead. Or was that it? Yeah, so being on the island or just off the coast of this island we were on, there were some really interesting effects of cold pools or katabatic flow running off, the island during some of the evenings, which was pretty noticeable. Having the multiple levels of the tower was super important for capturing that because the sonic anemometers at the top of the 10-meter tower sometimes didn't even notice a change in wind or temperature as a cold pool was coming through down onto the sea ice. So we definitely noticed impacts of the sea ice, and some of the turbulence scaling I'm doing right now is actually, it doesn't work very well if I don't filter for winds only off the sea ice or off the open ocean. So yeah, the impact of internal boundary layers was pretty strong throughout the campaign.
Thank you, Brian.
Mm-hmm.
All right. Well, thank you so much, Brian. We very much appreciate it.
Awesome. Thank you all.
And Dr. Chilson, if you want to go ahead and introduce Gus.
Sure. And just as a follow-up on what Brian was presenting, this is a lot to unpack in what he was showing, but I can emphasize that it is very important work. There's a lot to absorb. I was just sitting here thinking that one of the taglines of CAS should be conducting measurements and doing science that is over your head, because that's literally what we're doing. But now I'll take this opportunity to introduce Gus. He came to us from Brazil. He already had a master's degree when he came, and he joined us to work in electrical and computer engineering. So Brian is from the School of Meteorology. Gus is from the School of Electrical and Computer Engineering. And he just completed his master's degree working on the system that he'll be discussing. And has now transitioned into a PhD. So he'll be making great progress on a different topic as he goes forward. But a lot of cool things to talk about in what he was doing for his master's, and that's what we're going to hear about. So take it away, Gus.
Thank you. Does everyone have my presentation?
Yes,
right.
We can see it. Yeah.
And you can hear me as well.
Yes.
All right, cool deal. So as Dr. Chilson said, I'm a PhD student at the School of Electrical Computer Engineering. Under him, he's my advisor and also my boss at the Center for Autonomous Sensing and Sampling. I'm a native from Brazil, and today I'm going to talk about autonomous sampling of atmospheric carbon dioxide. Well, carbon is the building block of life on Earth, and a significant part of the carbon cycle occurs in the form of atmospheric carbon dioxide. Even though there has been significant consensus in the past 60 years around the importance of atmospheric carbon dioxide regarding plant growth, global temperatures, and even extreme precipitation events, there's still a knowledge gap regarding the intricacies of the relationship between atmospheric CO2, the biosphere, and weather patterns. One example of this gap is the Arctic permafrost, no pun to Brian's presentation intended here. But it's the Arctic permafrost that has always been considered a sink of carbon in numerical modelings for the global CO2 budget, but has been recently shown as a significant source of CO2 due to erosion. Difficulties in accessing these areas and risks to humans in part explain this knowledge gap. But the other significant part of it is actually the limitation of the current technologies. For example, if we look at satellites and instrumented towers, who represent the largest portion of publicly available data sets for atmospheric CO2 concentrations, we'll notice that they provide data 24/7 for large areas. However, if you look at towers, for example, they are limited to perform their measurements at fixed locations. And we don't have any information of what's happening above the tower or even between the towers. Satellite data helps fill that gap, but satellite retrievals ranges sometimes are limited by weather conditions, and sometimes they're not able to perform measurement near the surface where we live. Because of the mobility and autonomy of small unmanned aircraft, in my master's thesis, I proposed a UAS-based sampling system to complement the existing technology and perform initial exploratory studies in undersurveyed areas. To make this new system truly helpful in reducing the knowledge gap, it needed to be cheap and accessible to as many people as possible. When designing a UAS-based atmospheric sampling system, one is presented with many choices. Within the spectrum of sensor integration alone, you can, for example, look at the lowest level, which would be attaching a standalone sensor to an off-the-shelf aircraft, and the highest level of integration would be, sensor integration directly to the flight controller on a custom-designed aircraft for that specific type of measurement. And there's no right or wrong per se. For example, a standalone sensor strapped to an off-the-shelf aircraft is quick to develop and naturally platform agnostic, which is great. However, it will never allow you to perform, for example, adaptive sampling. So developing your system around an open source commercial flight controller is a compromise solution that leverages the benefits of a flight controller level integration with the modularity and cost effectiveness of a standalone sensor. The PixHawk is an open hardware design standard that, through a licensing system, allows companies to manufacture and market interchangeable flight controller boards. This allows researchers and developers to have industry support without being tied down to a single company. Another advantage of the PIXHawk project is its compatibility with two major open source flight control softwares. One of these two is the Autopilot, an autonomous vehicle control framework. Well, some other important considerations for this project were cost, size, and weight. After all, the thing had to fly, right? So the Sensair K30FR is a non-dispersive infrared carbon dioxide sensor that, despite the plus or minus 30% reported data sheet accuracy, at the time was the most accurate low-weight, low-cost sensor available on the market. Using the PIXHawk Q Black flight controller and the K30FR's communication interfaces, I started to develop the lower atmosphere carbon dioxide acquisition system, or LACAS for short, as that referred compromise solution. The modularity aspect of the proposed solution is naturally occurring once a composite design pattern is combined with the Autopilot's vehicle type architecture. After the project was forked and the sensor integration code was written as a native library, all the vehicle binaries compiled from the CAS Autopilot repository were composed of the vehicle-specific code and the firmware, the framework shared code. In this case, the LACAS library and the CAS common code. As a quick note, the CAS common is code that is shared with the Copter sound project that Brian referred to and Tony presented 2 weeks ago, and is what enables all CAS aircraft to transmit sensor data from the aircraft to ground station computer in real time through the flight telemetry data link. Perhaps the most important aspect of the LACAS library was the ability to isolate the sensor communication from the other sensor activities. The PIXHawk provides a secondary I2C bus on a separate thread for all non-flight critical peripherals. This is done to maintain vehicle safety and protect the flight control. But due to an impedance incompatibility between the SDA pin of the PIXHawk and the SDA pin of the K30FR, I was not able to integrate the sensor using the I2C bus. Using the secondary telemetry and GPS ports of the PIXHawk, I was able to develop a UART integration for the K30FRs. But because the UART hardware is responsible for controlling the flight control surfaces of the aircraft, isolating this code from the remaining sensor activities was crucial. This architectural design, the architectural design of this library has like many other interesting features that perhaps I can detail in a future seminar. But for the sake of time, we'll move on and consider that when one is developing a US-based sampling system, one must also consider the possibility of the aircraft contaminating the physical attributes being measured. Sensor placement is critical because it can affect airflow over the sensors, body frictional heating, solar radiation heating, motor-induced heating, propeller layer mixing, amongst many other parameters. So for the fixed-wing deployment of LACAS, I designed a 3D printed intake scoop that houses 3 temperature sensors and 3 humidity sensors for an improved detection of the boundary layer thermodynamic structures, as well as a gas intake for the carbon dioxide sensors. Considering that the Sensair designed the K30, not for a UAS application, it expected to live in a perhaps industrial environment. Carl, who's here representing Sensair, can correct me on the questions and answers later. But it was definitely not made for the deployment in the UAS environment. So to go around this, what I did is I tried to miniaturize the natural environment where a K30 would be deployed, and manufactured also a 3D printed miniature chamber for 2 K30FR sensors. Because this design created an isolated environment for the K30FR, a temperature and humidity sensor was also placed inside the mini chamber to evaluate if the temperature and the humidity of the air parcels were not being affected by the plumbing and the mini chamber itself. The LACAS mini chamber has a reduced volume that exposes only the K30FR's optic chamber to the controlled airflow. And this is important to give the system a high sampling spatial resolution. After all, the integration of the sensor to the autonomous flight controller allows the system to time and position stamp each measurement of the aircraft's GPS with the aircraft's GPS data. The measurements are logged by the flight controller with all other flight control variables, pitch, yaw, motor RPM, etc., and transmitted in real time to a ground station computer through the flight telemetry radio link. This allows the CAS scientists to monitor the atmosphere while the aircraft is autonomously performing the pre-programmed mission. And here's a quick peek on how the system looked when we installed it in one of our development fixed wings. And you can see that it provided a pretty clean and well integrated form factor. And again, going back to this idea of this compromise solution, one of the interesting things is that because of the integration strategy adopted and the proposed architecture of the LACAS library, the system was able to be deployed on a Copter without any changes to the sensor code itself, just by recompiling the code as an ArduCopter instance of the ArduPilot framework. You can see in this picture that this version of the system used the thermodynamic sensors housing scoop from the CAS CopterSon 2.5 with an adapted gas intake. So to evaluate the effectiveness of this design, 4 24-hour tests against an LI 840A benchtop gas analyzer were performed inside the CAS lab. This screenshot taken from the LACAS desktop application shows that in a 7-hour interval with few abrupt changes in ambient concentrations, LACAS reported a root mean square error of plus or minus 1.10 ppm. And during the same test in a near 2-hour period with abrupt concentration changes, the system reported an RMSE of plus or minus 2.06 ppm. To further investigate this design, the system was taken to the Oklahoma Mesonet Calibration Laboratory and put through 3 calibration chamber experiments to study the impact of temperature, humidity, and pressure on the system. If any of you wish to see more details about these experiments, at the end of the presentation, there will be a link to my thesis. And after promising results in the lab, it was time to take the system and test its capability of actually complementing these other instruments, which was the reason we tried to create it. So in 2019, LACAS was deployed in a conceptual field experiment at the Kessler Atmospheric and Ecological Field Station, a 360-acre research facility located in Purcell, Oklahoma. Installed at Kessler are the CAS Tower on the right, which is a 10-meter tall structure measuring CO2 concentrations with a gas analyzer through a 4-level multiplex pump system built by William Doyle. And the Kessler Flux Station on the left, measuring CO2 concentration levels and CO2 fluxes amongst other parameters at the 2-meter level. Besides these 2 instruments, Kessler is also home of the Washington site of the Oklahoma Mesonet system. This is an instrument installation that measures physical parameters ranging from soil moisture to wind speed and direction at the 10-meter level. Well, this conceptual field experiment had two goals. The first was to evaluate LACAS' ability to augment the instrument at Kessler, and the second was to evaluate LACAS' ability to detect seasonal changes in the vertical structure of atmospheric CO2 concentration. The aircraft was programmed to perform a stepped spiral ascent following the highlighted perimeter over the referred ground instruments. This stepped spiral ascent creates a stack of slices of the atmosphere that represent a vertical extension of the ground instruments, because the aircraft is capable to fly at the instruments level for comparison and then fly above the instruments, creating this virtual extension. The flights for the field test were performed in 11 days for over a 5-month period from May to October of 2019. Each flight, they started 30 minutes before sunrise and went until 11 in the morning. These hours were chosen in hopes of capturing the impacts of the boundary layer's morning transition on the vertical structure of atmospheric CO2 concentrations. The scientific results for this experiment are currently being analyzed by meteorology undergrad research assistants under the 4-year research engagement program. And even though I'm not a meteorologist and I'm not a chemist, I'm going to attempt to show you some preliminary results. So bear with me. Well, the screenshots from the LACAS desktop application show here the raw concentration values for flights on May 30th and June 7th. So again, these are raw values without any environmental correction or filtering. You know, this is straight the output from the aircraft. And it's interesting that we can, comparing the two dates, the May flights and the June flights, we can already observe a significant change in the temporal evolution of the vertical structure of the atmospheric CO2 concentrations. And we believe this is due to the impacts of the boundary layer structures changing over time between May and June. So as a quick data sanity check, we can look at the first flight of May 30th, and it provides us a little bit more confidence in the observed structures when we look at the left panel, which shows the vertical profile of CO2, and the right panel that shows the vertical profile of temperature. And both of them, and both profiles present the same boundary layer structural feature at similar heights, possibly corroborating the preliminary results shown on the previous slide. So from an engineering perspective, the test was considered successful, with over 80 autonomous flights performed to 5,000 feet without an incident, and the preliminary results indicating that the system could have possibly captured some interesting atmospheric features. I think that very soon, Dr. Pilar Little and the students from the FIRE program will have a full presentation on this data set, which is going to be very interesting to see. So in closing, I would like to say that this presentation illustrates a very small portion of a very long and methodical process of development, testing, analyzing, and redevelopment. The system is being developed for the scientific community, and I hope to grow it with the scientific community. This work was presented and well received at the conferences of the American Meteorological Society, the International Society of Atmospheric Research with Remotely Piloted Aircraft, and the American Geophysical Union. Many of the feedbacks received from the community are being incorporated into the system. And finally, I would like to thank the Oklahoma City Innovation District for putting together this event, the Advanced Radar Research Lab, and the Oklahoma Mesonet for their facilities, and the National Science Foundation and the CloudMap Consortium for their financial support. If you have any questions that were not addressed here, please feel free to ask them now or email me directly. You can also email the Center for Autonomous Sensing and Sampling. If you want to know more about us or receive updates on our research, please visit the website and our Twitter. For full details on this project, my thesis is available for download at the ShareOK website. So I thank you very much for your attention.
Thank you, Gus. Does anyone have any questions? We do have a few minutes for Q&A.
So this is Carl Bengtsson. I'm the Technical Director of Sensor North America. I don't really have questions as such. I just want to give a thank you to Gus for inviting us. It's always very interesting to see when academia or other institutions use our sensors in non-intended applications. Gus talked about earlier, the K30, back when it was first developed, was intended for indoor air and indoor installations in typically light commercial residential buildings. So this is always fun to see when it's being put to the test so far, and it's been used in quite a lot of outdoor environmental projects now. But if anyone is interested, they can feel free to reach out, and we can kind of share the kind of publications the K30 and other types of sensors has been used in, and we can take it from there. So thank you, Gus, for inviting us, and it's been very interesting to see these results. Thank you.
Yeah, a quick comment on that. I think the invitation fits very well for the kind of environment the Oklahoma City Innovation District tries to create, because you guys were great when I had a bunch of questions of how far could I push it. And so this partnership of academia and industry is pretty cool. And I was very thankful that you guys were so quick to respond, send other papers, and collaborate.
Yeah, no, thank you. I mean, like I said, let's keep the momentum and pick up what else we can do with our sensorics and these types of applications. As you know, we have, well, we mentioned a few already, so let's see where we can take this.
Any other questions for Gus? All right, any closing comments, Dr. Chilson, that you'd like to offer?
Yeah, thank you. I would like to highlight the fact that these small UAS do offer a fantastic opportunity for conducting research that really has been inaccessible or unavailable to us in the past. There's been numerous campaigns to study stable boundary layers, to study CO2 concentrations in the lower atmosphere, and and other applications, but every one has its pros and cons. And I'm not saying that this technology also doesn't have its pros and its cons, but I think for the first time, there's a large collection of atmospheric scientists and atmospheric chemists who are really excited about being able to collect measurements in that lowest 1 mile, 2 miles of the atmosphere, which has been so hard to access. And so anybody and everybody, both from the university side, the industry side, to the extent that we can come together and address this problem, it's really going to, I think, have big impacts on what we can do as a community. So I really appreciate the opportunity that you and your cohorts have provided for the students and to present and for us to introduce CAS. And yeah, that's all I have to say.
Thank you so much. And thank you everyone for joining us today. Thank you to Brian and Gus for your presentations. please, when you have a moment, head over to our website, okcinnovation.com. You can sign up for our newsletter there. We'll actually have our next issue going out next month. So hope to do some recaps of these presentations and some other things that we have coming up. You can also follow us on social. We're on Facebook, Twitter, Instagram, and LinkedIn. But again, thank you everyone for participating today, and hope all of you have a wonderful rest of your week. So thank you.
Thank you, Megan.
Thank you so much.